Assalamualaikum and good afternoon to the madam and all the students. Today I would like to present about the characteristic of the distribution, which is integral relationship. Sometimes resident time distribution ET is called the exit age distribution function. If we regard the age of an atom as the time it has resided in the reaction environment, then ET concerns the age distribution of the effluent stream. It is the most used of distribution function connected with reactor analysis because it characterizes the length of time various atoms spend at reaction conditions. The first equation is to find the fraction of molecules exiting the reactor that have spent a time t or less in the reactor. And the second equation is to find the fraction of molecules that have spent a time t or greater in the reactor. The F-curve is another function that has been defined as the normalized response to a particular input. Alternatively, the following equation has been used as a definition of Ft, and it has been stated that as a result it can be obtained as the response to a positive step tracer test. Sometimes the F-curve is used in the same manner as the RTD in the modeling of chemical reactors. So we can find the Ft using the same method like ET, which is we can use area under the graph or Simpson. For the example, find Ft and the fraction of material that spends 25 seconds or less in the reactor. From the graph, we can be divided into two shapes, which is triangle and trapezium. For the area of trapezium, we can get 0.375 and the area of triangle is 0.5. So the total of the area is 0.375 plus 0.5, we can get 0.875. So the cumulative distribution function Ft that spans 25 seconds F25 is 0.875. Lastly, to get the fraction of the material that spends 25 seconds or less in the reactor, the Ft times 100, which is 0.875, times 100, we can get 87.5%.
I'm going to explain about the mean residence time (TM) in RTD. The definition of mean residence time: the residence time of a fluid parcel is the total time that the parcel has spent inside a control volume. Example, a chemical reactor. The residence time of a set of parcels is quantified in terms of the frequency distribution of the residence time in the set, which is known as residence time distribution (RTD), or in terms of its average, known as mean residence time. For an ideal reactor, the space-time or average residence time defines as V over V if there is no dispersion or diffusion in the reactor. Second, the mean residence time is equal to nominal holding time, either in ideal or non-ideal reactor. Third, ET is defined as the first moment of RTD function. Hence, the formula and the graph of mean residence time is shown as for the second equation, which is space-time equals to mean residence time, T equals to Tm. It is only used to calculate constant volumetric flow rate. It is only true for closed system. The exact reactor volume is determined by this equation, V equals to V mean residence time. Besides, space-time equals to mean residence time when only two conditions are satisfied. First, no density change. Second, no backmixing. Backmixing means the tendency of reacted chemicals to intermingle with unreacted feed in reactors, such as stirred tanks and packed towers. The last part is the calculation of mean residence time. So this will be the example of calculations to evaluate mean residence time. The table will be given with values, or we have to calculate from the previous table given. By referring values in the table, we have to use formula of mean residence time. As we can see, first we need to integrate from 10 to 20, second equation from 20 to 30. Then we have to substitute the values by order in the formula. Finally, you'll calculate and get the answer of mean residence time Tm, which is 20 seconds.
Alright, I'm gonna explain about other moments of RTD, which is have three moments. The first one is mean residence time, Tm. The second moment commonly used is taken about the mean and is called the variance or square of the standard deviation. It is defined by variance equal to integral 0 to infinity t minus tm the power of 2 et dt. The third moment is also taken about the mean and is related to the skewness as the power of 3. Alright, the next one is RTD for ideal reactors. The RTD of a reactor can be used to compare its behavior to that of two ideal reactor models, the PFR and the CSTR or mixed flow reactor. This characteristics is important in order to calculate the performance of a reaction with known kinetics. RTD is divided by 2, which is RTD in PFR and RTD in CSTR. For RTD in PFR, fluid entering the reactor at time will exit the reactor at time T plus T, which is is residence time of reactor. It is defined by ET equal to delta T minus T. And then for RTD in CSTR, an ideal CSTR has an exponential residence time distribution. Effluent concentration is identical to that of reactor contents. It is defined by ET equal to 1 over time exponential 1 over time. Thank you.